Okay, so then why can't I do this again? Okay, time to continue a little bit. Right, almost done for today. Right, so we should at least finish this part, and then we can go to the practice again, where you can ask questions. So we're here again. Let me see the streaming. Streaming is working or not? Streaming seems to work. Very good. Audio also works. And again, so the TA asked me to remind you, you have to finish the teaching survey. Please finish the teaching survey. The TA has a list. The TA has a QR code, so you can go to the TA. We will try later to put the QR code on Cyber University. We will not put the QR code now on YouTube where everybody can see it, right? Because that would be just chaos. So we are back here on the integral part. We have the general structure of the integral with the correct integrand here. What we need to do is later plug in the actual function for y. Now the radial part works similarly. We can just see what we do here. So we have integral r theta 0 to 2 pi and r from 0 to r0. That is all fine. Actually, need this. What else do we have? We had this already, right? The adjoint part, right. So next we can then go closer to the actual problem at hand. And if you scroll up, our y function only depends on the cosine with a few prefactors, you see? So these are just numbers, constant, but the actual function is cosine of an angle. So we go down over here, and then we now a bit closer. We have cosine, sine, cosine. Now, why is there an adjoint here, or complex conjugate? Because cosine is a real value function, so the adjoint or complex conjugate is the same. Now I plug this into the function. I will see I have a trigonometric product with different terms in the exponent, sine and then cosine squared. Who is confident that he or she or whoever student can actually integrate this function? Can be done, right? So this one, yeah, maybe partial integration or integrate by parts, or we ask Python to do it. Wait a little bit. So we get is 4 pi divided by 3. That's not too bad, right? This could be right. So now about the prefactors. So our angular part was, as given above, square root of 3 over 4 pi cosine theta. So our y function is now properly described, and then we take this angular part, we form its adjoint, so the complex conjugate. We multiply it with a function, and we multiply it by sine theta, sine theta. And we again perform the integration. This time again, magic will happen. Hopefully. Look there, it's just 1. Okay. So remember the question we started with was, is this spherical distribution function normalized? The normalization condition is, hey, when we integrate over all space, we get 1. We use the product ansatz to separate the function in angular and radial part, and the product ansatz allowed us to separate the integrals in integral for the radial part and integral for the spherical part. And now we see that the angular part is already 1. So the angular part is normalized. Now we just need to look into the radial part. There's also one line that uses the integrate method, not the integral, combined with do it, and it also will work. So now the radial part. So the radial function is given above again. We scroll up. I think it was r times exponential function of minus r, divided by a constant. So what we need to do is now define our radial part, plug it into the integral or the integration machinery, and see if it is 1 or not. So let's slowly move toward it. And I normally start with integral to display the integral. And what we have is our function. That is the function of r, which I call here, the object is radial for the radial part. That represents with an r and takes the argument small r. So I take the function, I multiply it with its complex conjugate through the adjoint method. And I set the integration from r, the integration over r from 0 to infinity. Right? So remember these two circles here, the two O's are infinity. And also do not forget to multiply the upper square term that comes from the change of coordinate system from Cartesian to spherical. Okay, but I think from now I need to have here SymPy 0, 0. No, it's imported here already. No problem. From SymPy import infinity, right? Two O's. So what else we need to do? We had a symbol in the expression above for a constant that was set a0. It's a distance. Distances are positive and have real valued numbers. When we have defined a0, we can now define the radial function, rad. And that is r divided by prefactor times the exponential function of minus r divided by 2a. We execute and we confirm that all the paths are there. Very good, right? And now the integral. Again, we have the radial function times r squared times rad. There's no complex number in that function yet. So if I use simply adjoint or just the integral, it will be the same. Just to make sure, simply adjoint. We can make one adjoint. We can look at the integral. We can integrate it. And later on, we can confirm our integral result with the do it function. So simply integral do it will give us 1. So now the question is, did you see the integral just now? Who can integrate this from 0 to infinity? It's a little bit hard, right? You should practice, right? It's again integration by parts. But in the end, you should see, when you do it yourself with pen and paper, that this integral takes the value of 1. So far, so good? And now we can put everything together. So when you put everything together, it becomes a little bit hard to read. But here we have an integral for the product, the radial and angular part, times the function radial angular part, times r sine theta, that is from the volume element, and then 1, 2, 3 variables for the integration, including the integral boundaries. And when I execute this, I see this beautiful integral written there. And then I can even execute it. Maybe I do this over here. You can play with the other 2 lines of code. Important to note is, do we answer the question? And at this point, yes, we have answered the question, because we see that integral defined above for the chosen function turns out to be 1. Therefore, we can say function is normalized. So far, so good? Can you all do this now? Yes, you can. Right, and now I tell you a little secret. So that function is just from like the quantum mechanical solution of the hydrogen atom. So you basically, whatever function you get there, you can check now if it's normalized or not. And it's not very difficult to do that, right? Because we use Python to do most of the heavy work. We just need to tell Python, take correct paths. Okay, and then, so the next part is Taylor series expansion, which is another important toolkit in a Mint subject you must have. So Taylor expansion is one of the basic things you need to know. Shall we do this next time, or shall we do this today? Do you want to practice a little bit more? What do you want to do? No. What do you want to do? No. No. Okay. Okay, so you want to practice? Hands up. You want to Taylor expansion? Hands up. Okay. Okay, good. Taylor expansion it is. So Taylor expansion is Taylor expansion is a really useful tool. It's why do we use Taylor expansion? Because sometimes things are just too complicated for us, and then we throw Taylor expansion or any other expansion to make our life easy. However, Taylor expansions, I fear, sometimes are a little bit confusing for students. So what I observed is actually you can write down this formula, right? Then you have your few cases that somebody showed you to do, then you know how to do those. But I give you something else, you're like, what do I do now, right? And this is a sign for me, well, maybe not you, but I've seen this in previous years, right? So remember the procedure, practice, right? Many of the things are practice, practice, practice. And here now you can use Python to help you getting the Taylor series extension. So shall we go through this a little bit here? Have you seen something like this before? Where is my laser pointer? I always get it from the department office, and then I think I always forget to bring it. Put my office somewhere, and then. Okay, so Taylor series expansion, what you do. First thing is you take the derivative, right? So this part here, right? Take the derivative nth order of the function. First thing. Then you plug in a value, a point of interest, like x equals 0. Then you multiply it with the factorial with the same n as you did the derivative here, and then you multiply that with x minus your interesting point to the power of n, and you do this for many starting from 0, right? Seen before, done before, yes, no, maybe? So when I give you now e to the power of cosine x, you can do the Taylor series expansion, right? Shall we do that? So that everybody understands me. I want that you do sim pi of cosine of, what did that say? x, and this you put in the exponent of sim_pi.x, right? Can you Taylor expand me this around x equal 1? Here, looks like this. A little bit. So here. Can you Taylor expand this for me at x equal 1? Hands up? No? No, not heads up. Hands up. Hands. Not heads up. But I appreciate the heads up as well. So this one here, for example. Do you know how to do Taylor expansion? A little bit difficult, right? Luckily, we have Python today. But again, so the Python you use to get help, but in the end, it's always the person who does the work, right? So practice, 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 and use Python here as a tool to practice, right? To improve your skills. So choose an x, do the derivative, plug in the value, multiply it with a polynomial prefactor, and then go to the next and repeat it until you're happy. Here we have an example of x around x equals 0, and we know this is can be written here in this geometric series, right? That is defined for values for small x. Okay, here's another example. Exponential function, another series. Right. Seen before? You know how to do? Okay. Is that right? So the application of the Taylor series expansion, you know from physics, this is 7th grade, maybe? The 7th grade. So the original function reads like this. It's a differential equation, second order in time, right? Where g and l are gravitational acceleration and distance, and then we have a displacement angle here that is 0, and then we use Newton's mechanics to basically find a relation between forces and acceleration. However, this is a little bit hard to solve. Try it. I think this was only solved in this form after the year 2000. So I have the number 2007 in mind. Somebody used elliptic integrals to solve this, but before this it was not. So what actually is done, where is it? We do a Taylor approximation, and then we approximate this one here just as done. I thought I had that somewhere. Is it? Right, in the end, what you do use in high school to solve this equation, this one. So you Taylor approximate your variable and you drop the sine function. Good. So let's see. And then we want to do the same thing, but we want to use Python to actually help us with the Taylor series expansion. How do we get Taylor? Well, we use the so-called series method. For the series development, we can specify the point of interest, we can define how many terms we want to have, and so on. What else do we need today? We need to have some SymPy plotting routines because the Taylor series expansion is an approximation. And we always need to verify is our approximation good enough, right, accurate enough for us to work, or do we need to put in some more work? So how does the plotting work? Well, define a function, SymPy x. Remember, we don't have specified any values for x. And then we just call SymPy plotting plot get. And that's the rest. So we will see the plot in a few seconds. Meanwhile, we go to the SymPy here's the plot. SymPy series. So we need to provide it with an expression that we want to Taylor expand, the point of interest, and how many terms. So here is a simplified syntax, right? Expression, the standard point x0 is at 0, and the standard value for the number of terms we want to do the expansion 4 and 6. We can change the optional arguments here, but we must provide always the required argument. Okay, so let's see. So we have here two symbols, x and x0. We have some unknown function labeled f. It's a real-valued function with the argument x. So far, so good. So you also can Taylor expand an unknown function. Isn't that a few typos here? Isn't that interesting? You don't even need to know the function to Taylor it. So when we do now the Taylor expansion around x0, right, 3 terms, we will see that we have the 0 order term, right, just function value at that point, the first derivative, second derivative, third derivative, second, 1, 2, 3, second derivative. So here is the function evaluated at x0, just the function value. Then we have a linear polynomial term, x minus 0, times the gradient. And then we have the quadratic term times the, well, something related to the curvature of that function at that point. So far, so good. Note that here I used remove O to not display higher order terms. When I have G0 and we Taylor expand, we should normally indicate with a mathematical O that there are other terms we have ignored, because we hope actually that there are more, at least in the expansion near our point of interest. Does it do something? I need to call what is G1, right? There we go. Okay, so now in the next example we can change a little bit, right? So you see here we have order O terms for higher terms, but we don't have to give this. Go back. So we also can change now the point of interest or the number of terms. Here there is 2. You can put it to 20, you can put it to 40, you can put it to 1, right? Whatever you desire, whatever makes sense. Okay, fourth order, and so on. So now when we apply this to the sine function, right? Wait a little bit, I think it's done, right? Okay, so we here define sine function as SymPy sine. Then we have an order 2, and we have a Taylor object that takes the result of the series on my sine function. Order is given here as 2. The point of interest is now 1.8 for whatever reason. And we apply the remove to remove the higher order terms. And then the same thing again with another value of number of polynomials. But we execute and we plot the sine function. So far, so good, right? Now, when I look at my Taylor 2, I have now the function value available, right? I will see it's a linear function because you can evaluate the value of the gradient of the sine function. Looks like this. Then I can plot Taylor 2. Does it look like the sine function? No, it doesn't. Then I can look at my Taylor 10. And there will be a lot of terms because that is a polynomial basically that goes up to the order of 9. So far, so good. Then I can plot Taylor 10. Does this look like the sine function? I mean, a little bit maybe here between from 0 to like 5 maybe, right? Okay, so maybe more higher order helps me. So what I do now is I put order 100. So far, so good. Execute. This might take a while. And then I plot order 100. What we also could do is take our Taylor function and overlay it with sine function. So plot two functions, right? The original and the Taylor. And then you see even better that, yes, there is more and more agreement between the Taylor function and the original function, the more terms you add. So this almost looks like a sine function, right? Yes, no, maybe. And the only thing you need to do is you need to have like 100 terms of your polynomial. Okay, that being said, in plotting, you also can change the x and y limits that are here wisely adapted. And so here's my result of the Taylor expansion. Okay, but from minus 20 to 20 doesn't do it. What you should take away from this is it's very, very simple to call the Taylor series expansion now, and you have a great tool at hand for your future studies. And next time then, yes, we complete this because we can repeat Taylor series expansion 2 weeks. It's very important. It's very useful. So yes, we do that. Comments, questions? And since we wanted to do exercises and Taylor expansion, we still have 20 minutes for exercises. Right? So you can practice a little bit. The TA. This is supposed to be after the lecture, right? Sure. So I stopped